So I told you at the start of the year that you didn't know what a statistic was. And we're sort of going to tell you today what it is. Okay? So a statistic is not just a number. It's not just data. So it's not how many free throws you made last night in the basketball game. Okay? A statistic is a number that we use to describe a population. So we talked a little bit about the difference between a population and a sample. So a population would be everyone. Now a population could be all of the students at Emory High School. Right? A sample would be some subset of that population. So you guys are a sample of the Emory High School population. And the Emory High School population is a sample of all high school students in Utah or in the country. Okay? And we need to be able to distinguish between values that are populations and values that are statistics. And because of that, we've given them different variables. And some of the variables are really weird. And I don't know why they picked what they did, but that's what happened. So, the average of the population is lowercase mu. So if you talk to everyone, the entire population, and you calculate the average, the variable used for that average is lowercase mu, and it's spelled mu. So you might want to write that on there. It kind of looks a little bit like an N, or an M, a little side, I don't know, a messed up M, but that's a Greek letter. So other Greek letters, alpha, beta, gamma, delta, epsilon, zeta, eta, theta. There's mu. There's another one called nu, N-U, omicron, upsilon, rho, tau, omega. Anyway, lots of Greek letters. Okay. So if you calculate the average of a sample, then that variable is what we call x bar. So anytime you put a straight line over the top of a variable, that's pronounced bar. So the sample average is x bar. Then we move on to standard deviations. So the standard deviation of the population is calculated the way that we did it originally. You calculate the average, you find how far everybody is from the average, you square it, take the average, and then then you take the square root. Okay? And you're going to love this. This variable is lowercase sigma. And that never used to be funny until a couple years ago. And now kids laugh every time I say sigma. So all Greek letters have a capital version and a lowercase version. Both the parameter average and the parameter standard deviation are lowercase. I don't know what capital mu is, but capital sigma looks like this. Yeah. Okay. So. And lowercase pi looks like that, and capital pi looks like this. Okay. If you take the standard deviation of the sample, we have to use a different formula. So you find the average, you figure out how far everybody is from the average, square those values, and then we divide by, we don't divide by n, we divide by n minus 1. And what's the purpose for that? It bumps the standard deviation up a little bit, because if I want to know the average height of all students at Emory High, I'm probably not going to get a perfect sample, right? And the smaller my sample, the more mistakes I could make, the farther away I could be. So by dividing by n minus 1, I sort of cover the chance of making a mistake, right? And that is lowercase s. Okay? And then the proportion, so if you are looking at the entire population and you say 10% of the population likes Mr. White, then the variable for that is going to be pi, lowercase pi. Okay? But if you only look at a sample and you calculate the proportion, we call this p hat. That is the actual name, p hat. So today, you are going to go through this, and you're going to read the situation and decide, is this a statistic or a parameter? Okay, so that's pretty easy. But I want to talk to you a little bit about what it means to be a statistic. So let's say that mu for all females at Emory High is a height of 64 inches. So in order to find that, I would need to run around and talk to every single female and either measure them or ask them how tall they are, right? So that's like 305 people. That's tough, okay? Chances are I am too lazy to do that, and I'm just going to take a sample. So this would be the parameter. And as statisticians, we want to know what the parameter is. However, we want to figure out the parameter using as little work and really as little money as possible. So if you're paying people to run around and do these surveys, it's expensive. And sometimes you actually have to pay the people that you're measuring. Right? Come take this test, I'll give you $100. So taking samples is very time consuming and very expensive. So instead, I'm going to say, okay, 80 measurements is going to be fine. So for my sample, I'm going to say N is 80. So I run around and I talk to 80 females at Emory High, and I measure their heights, and I get X bar is 65.1 inches. Now, I don't expect that my sample is going to be perfect. The only way to get a perfect sample would be a really big sample. In fact, a sample so big that you talk to everybody, right? So, if you talk to everybody, that is not what a statistician does. If you are taking a census, then the statisticians don't have a job. Because a statistician's job is taking this number to predict what that number is. And that's a statistic. A statistic is a value that you use from a sample to predict what the parameter actually is. And there are a couple different ways that we can present this information, but if I take the sample, I'm going to get a standard deviation. So let's say that my standard deviation is 3.1 inches, right? I can use that standard deviation to create a window that will give me a pretty good guess of what the actual average is. If all you do is talk to a sample, there is no way to 100% know the parameter. Would you agree? So what we do is we say, okay, our best guess is 65.1. Okay? So I want to be pretty sure that the actual value is somewhere in here. And then figuring out how far this distance is, that's a statistician's job. Okay? And it's going to take into account two things. It's going to take into account how big the standard deviation of the sample is, and what else is it going to depend on? You didn't learn this, but can you figure it out? How can I be more sure? Are there samples that would be more trustworthy than other samples?
Yeah.
What would that depend on, other than whether or not it's a good sample?
Portion of outliers?
So yeah, you look at it and say, holy cow, this is really spread out. And that's going to, the outliers are going to be inside that standard deviation, right? But it's going to depend on the number of people you talk to. If you only talk to 5 people, how accurate do you think your sample is going to be? Not very. If you talk to half of the kids, it's going to be really, really good, right? So we have to balance how many people do we talk to. Because the more people we talk to, the narrower this window is going to be. So our ability to guess the true average is based off of how spread out our data is and how many people we talk to. Now we can't change the spread of our data, right? That's just inherent from the population.
Michael Elijic, please come to the office. Michael Elijic.
But we can talk to more people. So if we talk to 20 people, we might end up with a window that's this big. And we could say, this is going to sound familiar, I'm 95% sure that the true average is somewhere between 61 inches and 67 inches. Right? Is that very helpful? No, it's not. But I'm 95% sure that the true average is in there. So if I talk to more people, let's say I talk to 80, then I might be able to say something like, I am 95% sure that the true average is somewhere between 63.8 and 66.2. Okay? The other thing that I can do is I can change my confidence level. So instead of 95% sure, I could change it to 99% sure, or 90% sure, or 68% sure. And that's a statistician's job. So the statistician's job is we take this information, we look at the average, we take into account how many how spread out it is, we figure out how many people we need to talk to get a good value, and then we set our level, we draw that line, right? How far off does the dice have to be before you throw it away? And then all of that gets crunched together in this algorithm, basically, and it will spit out a value something like this. And we can say, we're pretty sure that the true answer is somewhere inside that window. Okay? And that's stats. That is what a statistician does. All right. So, was there anything in 2.2 you want me to go over? Don't remember? Okay, you do this worksheet, I'll review 2.2. If there's anything we need to talk about, we'll do that.